concept. So without further ado, Chris, take it away.
All right. Thank you so much, everybody. Um, hope you are all doing well here today. My name is Chris Cogswell, and we're going to be talking about what is sustainability. So, all right. I'm going to stop my video here. So, like I said, my name is Chris. I'm originally from the East Coast of the United States. I received my bachelor's degree in chemical engineering and philosophy from the University of New Hampshire before getting a PhD in chemical engineering from Northeastern University. And my research work really focused on improving sustainability through the capture and conversion of CO2 using nanomaterials. And we're actually going to be talking a little bit about that later on here today. But yeah, I hope you are ready to go ahead and get started. So really, we're all here today at the beginning of our sustainability series to answer the question for ourselves, well, what do we mean by sustainability? And for a lot of people, when you think of sustainability, I think we think about things like, conserving water, protecting the trees, not polluting, kind of, more like hippie kind of stuff, right? We're trying to protect the environment. We want to be good to nature and animals and everything else. But interestingly, actually, if we look at sustainability from the perspective of engineering content, what we'll actually find here, if I run this search for sustainability in Compendex, is if we actually look here at the controlled vocabulary or even classification codes, or if I pop these open, for example, what you'll notice is that there is a huge, variance in what sustainability can mean or how it's applied. Right, so here we have kind of what we all think of, I think, environmental engineering, water resources, soil ecology. But you can also see terms like nanotechnology, computer applications, mathematics, chemistry and inorganic chemistry, social sciences. So this field of sustainability really has a huge variance there. And so today, that's really what we're going to try and touch on. Another interesting aspect to sustainability is the fact that really, if we look at the years of publication, right, the years where this term pops up in Compendex, say, for example, you can see that really, although it took off in the late 2000s, this field has an extremely long history, right? So here we're going back to really the 1940s and even earlier, where sustainability or sustainable engineering was something that we were trying to think about and trying to figure out. All right. So sustainability really means different things in different contexts. So for example, sustainability in the United Kingdom is going to look different than it does in the United States because of our significant differences in things like, say, geography, population, politics, resources, etc. So if you think about, say, the United Kingdom versus the US here, we're so much larger here in the US. We have so much more forest coverage, and the population density is so different that, for example, our use of different types of fuels or different types of energy generating methodologies is really different than the UK. And it's because, again, sustainability between the two places means something different, right? So sustainability for a country is different, of course, than for a company, which is different than for an individual or for an entire field. So what we're going to be talking about here today is the idea of sustainability as our ability to avoid the depletion of natural resources in order to maintain an ecological balance. Another way of kind of thinking about that is the general philosophy: do minimal or no harm to the environment or others while promoting our economies and our human civilization. So for these talks and for our series in general, we're going to be focusing on sustainability from the perspective of an engineering firm or team. And the really nice thing about that is that that's really what our tools are built to do, right? So when you run a search for sustainability, say a novel or an engineering village, you're going to get stuff from the perspective of an engineer who's actually doing this sort of work. But really, in answering that initial question here, well, what do we mean by sustainability, or why has sustainability developed in the way it has? We really need to understand why the field exists in the first place. So if we think a little bit about the beginnings of sustainability, it really starts off with the Industrial Revolution and the use of chemistry and chemicals in our daily lives. And so if we think about, say, some of the chemistry that was available at the time back during the Industrial Revolution, some of it is comically dangerous, right? Things that we today know we definitely should not have been doing or taking into our bodies. So, for example, here, lead paint, right? Or using amphetamines to say fit and slim, using ultraviolet light sources for tanning and getting the glow of health. Cocaine toothache drops for your headache or toothache, or even the use of radium and other radioactive materials in makeup, famously in Thoradia, right? This sort of makeup line that said you would glow with health, but really you were glowing with radiation. We kind of started running before we could walk, right? And so we didn't really think about the effect that these chemicals or these things that we were making as a society would have on the environment and even on ourselves. And this really took off during World War II, especially in the development of what we today call the Age of Pesticides. Now, when pesticides first came out, they were a godsend. It's not a over-exaggeration to say that chemicals like DDT or other pesticides, insecticides, fungicides, herbicides helped us win World War II. This was one of the ways that we were able to eradicate things like, say, some measles in the trenches of these war theaters. However, again, we didn't necessarily understand or comprehend the dangers of these chemicals. And so, for example, although DDT was great in treating malaria or helping soldiers stay comfortable and safe in theaters of war, applying it at home, it turns out had unintended consequences. So you had these really interesting advertisements like DDT is good for me, or no flies on me thanks to DDT. We were using something that was really effective during war at home and assuming that it would be safe. However, spraying it on animals and on the environment and everything else had some really negative unintended consequences. And really, the thing that made those unintended consequences stand out and really be looked at pretty significantly was the work of Rachel Carson. Her book, Silent Spring, really brought attention to something that people at home, bird watchers, forest rangers, people who, fishermen, people who were just out there with nature all the time, started to find that actually, in areas where there was spraying of these chemicals, there were really negative health effects. And so in her book, she had some really great quotes. If you haven't read it, I really suggest it to you. But so, for example, here, if we're going to live so intimately with these chemicals, eating and drinking them, taking them into the very marrow of our bones, we had better know something about their nature and their power. So Rachel Carson's work led directly to the field of ecology and this idea generally of sustainability coming about, and then the creation ultimately of the EPA in 1970. Around the time in the 1970s, the EPA was started. We were having things like mass extinction events, right? So, for example, the Peregrine Falcon, an animal that I know I see fairly regularly here outside of Boston where I live, and I'm sure that some of you have seen them out on your drives or walks around nature, was almost completely eradicated in the United States. However, this work to try to preserve species and preserve nature by understanding these consequences has really led to a swing back the other way. And the American Peregrine Falcon is sort of an example of a success here that worked, where we were actually able to go from a species almost completely disappearing to now being relatively prevalent in certain parts of the country. Now, throughout all of this idea, and since the 1970s, we've continued to learn about the environment, our effects on it, how we can really work and engineer in ways that are useful and good for the environment ultimately. And one of the most important takeaways is the idea that the environment is not static, right? There isn't just the environment. It's actually made up of numerous dynamic systems that exist in tandem, right? And I'm sure many of you, I know I did when I was in school, were actually probably taught differential equations or advanced mathematics through the example of the duck or the hare and the falcon, right? Or the eagle and the hares. This system where if the population of eagles goes up, the population of hares goes down, and vice versa, and how these exist in an equilibrium. Well, this is true also just of almost every part of the environment, right? So we think about something as relatively simple, say, or not really simple, but ubiquitous as water. So in the water cycle here, we have water from oceans get evaporated, it runs down as rainwater. What we may not often consider is the fact that that rainwater then will pull in pollutants and other things that we have in the ground. It then gets fed into plankton and other plant life or other algae type life that exist in water systems. That then gets eaten by the stuff that is eaten by birds or by fish. And eventually we eat it, or even just in the water itself, it can affect these populations. So even for something relatively ubiquitous, water, it's very complicated, this system that exists. And of course, here, for example, we have on this case here with the plankton, dissolved organic carbons. Now we have to worry about the carbon cycle. We have to worry about metal cycles. We have to worry about phosphates and nitrogen and other compounds that do exist out there. So, all right. That is kind of why we need sustainability or how we think about it. But what can we actually do as engineers or as firms to think about more the measurement and use of sustainable concepts? Now, first off, if we want to change something, right, we're all engineers. If we want to change something, we need to be able to measure it in some way. So there's a couple of different ways to measure sustainability, and we're going to go through some content too that's available on Novel that'll showcase some of those sorts of methods of measurement. However, we can think about these three broad-based approaches. The first is what's called the triple bottom line, which takes into account here the economy, people and places or society, and then the environment and how they interact with each other. The circle of sustainability, which looks at, again, these sort of common things, but essentially measures them on an index for a certain area. Or, of course, the environmental performance index, which looks at, again, about the same sort of things, but measures them in specific ways, right? So, for example, in this case, for ecosystem, they have a big perspective there on climate change is a big issue, and so the reduction of CO2, right? So here that makes up about 13.2% of the score that goes into the environmental performance index. Now, this all seems really complicated, and it is, right? There's a lot of different aspects to sustainability, and more are seemingly added every single minute, right? If we thought about what it meant to be sustainable in the 90s versus, say, today, that scope has really broadened significantly. However, for most business and engineering cases, the three bottom lines framework is in my opinion, the most effective and useful. So we're going to think about three main areas here: the environment or planet, right? And that's things like conserving natural resources, protecting ecosystems, and protecting the economy and people, or rather protecting the environment always with the economy and people in mind to make sure that we are still operating in a viable space. The economy itself, or profit, right? That's kind of your traditional bottom line. However, you want to think about the total economic benefit provided by a corporation, not just how much money you make, right? So for example, if you're trying to think about, well, I want to build a new facility, part of that economic impact might also include bringing jobs to a new community or reinvigorating a local marketplace, or, right, there's a lot of other options or other places there that we can think about. So again, it's the total economic benefit, not just the bottom line. And you want to really build and develop, again, with the environment and people in mind to make sure you're doing things that are equitable and viable. And then people and places, or society as a whole. And that's where we're thinking about things like creating good conditions for our employees, for the local and world communities. That's where something like process safety management really comes into play, right? That's not often thought of as an aspect of sustainable engineering, but it really is an important aspect to this question. And of course, always keeping in mind human capital and the way that that affects economic development. And of course, too, another aspect of this that can be thought of as being part of this people in place bottom line, things like charity or other programs to promote social welfare. So if we jump back into the tool here, right, so we're going to jump over into Novel. There is a tremendous amount of content there. Now, obviously here, on Novel, one of my favorite things about Novel is the ability to create folders. Right, so I've actually created a folder here on sustainability, and what it has is a lot of different titles here, right? So practical sustainability strategies. This book in particular, I think, is really interesting and quite good here. It goes over some of the ways to embed sustainability into your workspace and your engineering teams. Talks about concepts like circular economies, green chemistry, making buildings effectively, going through a full life cycle analysis of materials or products. It really can be quite a good title there. And then some other selections here that I hope will be of use for you. What I'm going to do here is I'm going to share this in the chat. So I'll just copy this right over to the clipboard. And then in the chat here, I'm going to paste this in. And so what you'll actually be able to do is if you follow that link from here in the chat or afterwards when you're viewing this, if you follow that link over, it'll open up Novel for you, and it'll ask if you want to add this folder to your Novel account, and then you'll have access to all of these different areas here that we made available or I pulled out here. Now, there's a lot of other content here on Novel as well, right? So for example here, if we're thinking about the energy transition, right, one of the things that we actually created here was a Novel energy transition page that talks about here some of these ideas, right? So if I'm interested, say, maybe in geothermal energy, I can click on that and it'll pop open that search for me in Novel. I can also here go to trending research pages, right? So for example, here again, if I'm interested, say, in biofuels, I can click on this. It gives me some stuff there. So there's a lot of good content here. And so here again, I search for geothermal, right? And here we have 1,300 books and text, 7 tables, graphs, and definitions. In some of the later sections here that we're going to do, for example, on green chemistry or smart cities and infrastructure, we're going to go into more detail here on some of the content we have available. However, I did just want to give you a taste here on some of this information, right? On Engineering Village, similarly, we have a tremendous amount of content here. So on sustainability, I can say, for example, I'm interested maybe in sustainable development, planning, agricultural robots, decision-making, or energy utilization. If, for example, I'm interested in agricultural robots, I can click here. And then really the power of Engineering Village is the ability to actually go through here and filter out my searches, right? So kind of the normal stuff that we would do. All right. Now, before we end here, I do want to go through an example, right? So we can try to think through some of these problems. So let's think of an example from my own research work, right? So, okay, we have this new material, magnesium DOBDC, that can be used to capture high amounts of carbon dioxide from flue gas, right? So it captures about 14 times more than our current traditional methods. The synthesis of this chemical requires the use of significant organic solvents, water, high temperatures over a prolonged time, and the reactors have to be filled about 50% by volume. Post-synthesis, the chemical needs to actually be activated under vacuum and increased temperatures to make it so that it can actually absorb CO2. Right? So it needs to be post-synthesis treated as well. Now, the material has a pretty good yield, about 85% per batch, but you can't make it continuously. You have to do it in batches. So that means that you have to basically have a lot of people working pretty continuously to make this material happen, as opposed to it being a fully automated process. And once the material is created, it can be reused for a prolonged period of time. So you're not just making material, capturing CO2 and then throwing it away. You can actually capture the material, or you can capture the CO2, remove the CO2 from the material, store that someplace, and then reuse that solid to capture more and more CO2. So the question that I would love if you could please answer it in the chat is, do you think this is a sustainable process? Based on our three frameworks, right? Economic, social, and environmental, do you believe that this process is sustainable or not? And please open up that chat there and say yes or no. Sustainable if there are infinite amounts of MgDOBC everywhere in the world. Okay, good point there for sure. We got a no here. It depends. That's the good thing about open-ended questions like this. You can always say it depends. But it really does, right? Depends, of course, here. If it can't be done forever or used forever, then it's not sustainable. Interesting here. Any other answers? We're going to give it about another 10 seconds here, let's say. All right. I want to thank everybody here. Two is still there. What do we do with it? So it depends. A really good point, right? What do we do with all the CO2 after we've captured it? All right. Thank you all so much for your participation here. So, okay, let's think this through, right? So if we think about the economic side of things, some of the benefits, right? It's a new product. There might be a lot of white space for development and sales. Perhaps we can become an innovator in a new area, right? Nanoadsorbent, something that isn't necessarily on the marketplace yet. But there are challenges, right? One is the material might be really costly to produce. We didn't really talk about it, but similar products cost about $20 per gram. So that's a huge cost there to the company. On top of that, right, we're talking about absorbing CO2 from flue gas. Is there going to be retrofitting we have to do? Are there safety or compliance issues we just simply don't know about because it's a new type of material or new process for our company? In terms of the environment, of course, there's a benefit there, right? We can capture a lot of CO2. We can reuse the material over time. And since it's solid starting materials, or there are solid starting materials we would have to use, it's not necessarily environmentally damaging. However, we said we used organic solvents. Those can be very bad for the environment or the health of our workers. It needs a lot of energy for post-synthesis activation. We need a lot of water. Like was said in the chat there, what do you do with all of that CO2 that you absorb, right, or adsorb rather? How do you get rid of it? Do you just put it someplace? Do you have to reuse it? If we just capture it, it doesn't really matter if we can't put it anyplace, right? Do we want to make landfills of CO2 materials now? And in terms of society, again, we have some benefits here, right? We can help reverse global climate change. And of course, that same thing we talked about before, this is bringing in skilled workers who can help us produce this new material. It can create jobs. It can really overall make a benefit to the local community potentially. However, we do have some challenges here, right? It's a new chemical plant. If we want to make a new chemical plant, there might be siting issues. We don't know the health effects of these materials, right? And again, if we're going to store the CO2, well, what does that entail, right? That means a whole bunch of other societal issues we have to deal with, right? Where do we put it? Do we have to get more land? People aren't going to want this in their communities necessarily. So there's a lot of big challenges here. Overall, this process really is considered not really to be all that sustainable, right? Carbon capture and storage, although something that maybe can help us with combating climate change, simply storing the carbon over long periods of time doesn't appear to be sustainable. We don't know what we can do with it. And so a lot of research is going into things like the conversion of CO2 to other chemical products, right? The use of carbon from CO2 as a feedstock. All right, thank you all so much for your attention here. Now, we've noticed, or I hope I've made it clear how complex the world and answers of sustainability can be, right? Everything depends on other things. So it's really more of an all-encompassing mindset than it really is a single answer, right? Now, in that case here, in our next series, we're going to talk about specific cases of sustainability, right? Things like, say, green chemistry or smart cities or infrastructure. And throughout all of it, we're going to hopefully be showing you how to use things like the tools that we make available here at Elsevier to get that content or information that can really help you answer these questions on sustainability, right? And with that, I'm happy to take any questions.
Thank you, Chris. This was a pretty great overview into sustainabilities and a starting point for further investigation. So before we get into those questions, I'm just actually going to launch another quick poll for our viewers while those questions come in so that they have time to send those our way. And I'll just leave that open. It looks like you do have a question in the chat. It says, hey, Chris, I'm sure you already know about it, but Elon Musk has opened a challenge for maximum capture of CO2. If it can be scaled up effectively, by the way, your research is extraordinary. Oh, that's actually not a question, sorry. And that's good prize money too.
So yeah, I am aware of, thank you so much for the kind words. Yeah, I am aware of the Elon Musk challenge there for scaling up a CO2 capture process. It's actually really interesting, right? There's a lot of different methods out there that's, one of the things we didn't talk about too much, but actually one of those environmental cycles that happens naturally is the carbon cycle. And essentially what that is CO2 is released by us, right, when we breathe, or by other sources. Then plants take it in. But not only do plants take in CO2, but actually so do minerals, right? So for example, calcium minerals become calcium oxide. Um, and then when that calcium oxide gets kind of eaten up as magma, or brought in as magma, not really eaten up, but as it gets brought in as magma, it releases that oxygen, and that's how the carbon naturally is cycled through the environment. A lot of work has gone into trying to get CO2 to recycle that same kind of way. The challenge ultimately is that carbon dioxide, right? If we think about our chemistry, carbon dioxide is a carbon with two double bonded oxygens on either side. It's a linear molecule. It is exceptionally stable. It's really, really hard to break apart. So catalytic conversion of CO2 to other feedstocks, such as say like acetone or acetic acid or ethanol or whatever, that's like the gold standard for carbon conversion. And that's really where I think if we're going to be thinking about where does that CO2 capture technology go in the future, that's probably what we're going to see. But yeah, if Elon Musk can make it happen, great. Otherwise, maybe he'll just get us to Mars, which is also pretty amazing.
Great. Now, if you could answer in maybe a little bit less than a minute, so who's deciding really if something is sustainable? Because I know during the example that you mentioned that you were saying it's not really a sustainable process, but here Elon Musk is challenging people with a prize money to do this carbon capture. So where would we go to figure out like who makes that call?
It's a really good question. There are a tremendous different places that make sustainability goals, right? So I just searched for sustainability goals. It's something really only in the last, say, decade we've thought about. And there's already about 30,000 records and compendex on sustainability goals. It really is up to sort of, it's countrywide. So the United States, for example, has goals of their own sustainability. It's sometimes it's entire industries, right? So for example, the auto industry has some sustainability goals that they would like to meet. The oil and gas industry has sustainability goals. It can also be based on worldwide governance, right? So it can literally be like the UN climate accords, or again, the UN has a list of sustainability goals themselves that they also put out there. So really, again, it's a mixed bag. It's sort of, not only is it up to us individually to be sustainable, but it's also depends on what sort of company or what sort of work you're doing and where you answer to. So,
Okay, great.
but generally though, you'd be answering or looking to local or state places.
All right, well, that's all we have time for today. Thank you everyone for attending. Please note that the history of whiskey production has been moved to April 22nd. So our next webinar, which is sure to be very exciting, so please sign up and don't miss out on this, is the libraries are helping their authors navigate the road to publishing, find out how. It's a win-win situation. And we hope to have you join us then.